So we'll start with this topic, electrical network and Kirchhoff's law. As we know that generally any electric circuits will have the circuit elements. Circuit elements like it might be resistance, it might be the cell, might be a capacitor, it might be inductor, or all these circuit elements. So all the circuit elements, if there are many number of them, and if they are in a very complicated way, they make the connections, then such type of connections are very difficult to analyze as to how the current is flowing, how it all how we can analyze the circuit if there are very complicated way the elements are connected. So generally when such interconnections happen between all the elements, we call them as electrical network. And in an electrical network, if it happens that many currents come to a point, or either they come, enter, or they leave, and if they meet at a particular point, then this point we call it as node. So such many nodes can be formed when we come across the electrical circuits. Now to analyze such complicated networks, we have something called Kirchhoff's law, and today we will learn about the Kirchhoff's law, and we will see how it helps us to analyze the circuits, the electric circuits. So first we will be learning about the first law, or first Kirchhoff's law, which talks about analyzing a node. When we are talking about such kind of electrical network, let's suppose that there are many currents which are, some are entering, maybe some are leaving this node. So there are currents, suppose I1, I2, I3, which are entering this node, and I4, I5, I6, I7, they are the current which is leaving from this node, but somehow all these currents, all these 7 types of currents are meeting at this particular point, which we call it as node. So how to analyze such kind of current is given by Kirchhoff's first law. It says that if you have a steady current means the current should flow. It should not get accumulated in any part of the conductor. So the charges should continuously flow without any accumulation at any particular point or any point of this kind of circuit. It can be called as node, or it also can call as junction. So when in an electrical junction, Kirchhoff's first law says that all the current, the summation, the algebraic sum of all the current should be equal to 0. So it says that at a closed circuit for a steady current, all the algebraic sum of all these currents, maybe it's entering, maybe it's leaving, the algebraic sum of all such current at the junction should be equal to 0. So let's see what we can understand from here. So in this picture, as we have already known that I1, I2, I3, these are the current that are entering the node. Now I take all the current that is entering the node as positive, and all the current which are leaving the node as negative. So I1 plus I2 plus I3, these are the positive current, and I4, I5, I6, I7. So these are all the negative current I have taken as negative. So when I sum all this thing, this total sum is going to be 0. So if you add all this current, the positive and negative totally, the current will be at the junction, all the current summation will be 0. So from here, this is the first law of Kirchhoff current law. From here we can very easily, we can just say whatever is a positive current leaving it. I can also write all the negative current taking to this side So from this particular, this is a Kirchhoff's law. From there I can derive another conclusion, that all the positive current or all the currents that are entering, the sum of all the currents that are entering is equal to the sum of all the currents that are leaving. So this is another point that we can draw as a conclusion from Kirchhoff's first law, or some places we can refer this itself is a law, that the sum of all the currents that are entering the junction and sum of all the current that are leaving from the junction are same. So this gives us one very interesting thing, that suppose if you imagine, suppose there is a particular flow at a particular junction, there is a flow of current, some are entering and some are leaving. So this particular currents that are entering, the sum of all the currents that are entering this node and sum of all the currents that are leaving the node, both are same. It means it actually analyzes that conservation of the current, all the current together that is entering the node, same amount of current is leaving the node. There are no current which is stuck or which is piled up or which is accumulated here. So it shows conservation of current law or conservation of flow of current. So this is what is Kirchhoff's first law. Now coming to Kirchhoff's second law. So before we go to second law, this particular law is about a loop or a mesh of the current circuit. In the sense, suppose current elements are placed in a way that it creates a path for the current to flow in a circular way or in a particular closed connection, then we call it as loop or mesh. So suppose let's take a particular case where I have a element, like I have a cell here and a particular, suppose it has both and again this is a circuit, and let's suppose this is A, B, C, D, E, F, R1. This is a cell and it has a EMF E1. This is R2. This has EMF E2. This is R3. Suppose current I1 is flowing like this, I2 is flowing like this, I3 is also flowing like this. So in this case, in such case, you see there is a loop, there is a close connection. So in this way, how do we analyze the path or the flow of current? So that's given by Kirchhoff's second law, and Kirchhoff's second law says that if there is a mesh or there is a flow of current, then the sum total of all the EMF, there are EMF in the circuit, then the sum total of all the EMF plus the total of all the voltage drops, that is suppose I current and R resistance, the sum total of all the voltage drop, this should be for a closed loop 0. So if the current is flowing in a loop or in a closed loop, then inside the loop the sum total of all the EMF plus the sum total of all the voltage drop together should be 0. So let's analyze this for this particular case. So first we will take this part of the loop, which is A, B, E, F. So A, B, E, F in this particular loop. Before going to analyze, we have to take certain thing as convention. When we are taking EMF, if the current is flowing from small line to big line, that means current is flowing from negative of this to positive of this. If current flows like this, then EMF is positive. We take it as positive. if the current is flowing from the positive to negative in this higher potential to lower potential, then we take EMF as negative, right? So this is about the EMF of the cell. Now coming to the voltage drop, if the current is flowing in this lower potential, that is higher potential to lower potential, higher potential to lower potential, then that is the positive to negative, then the potential drop we take it as negative. If it is from high to low, then potential drop will be negative, otherwise it will be positive, right? So first let's calculate this particular loop, which is A, B, E, F. So in this case we have two resistance R1 and R2, and the voltage drop in this case is I1 R1, in this case is I2 R2, and we have one EMF E1. So we have one EMF E1, we have I1 R1 voltage drop, and we have I2 R2 voltage drop, and the summation of all this should be equal to 0 according to Kirchhoff's law. But before that we need to take the particular and proper sign. As you see, this is the higher potential and this is the lower potential. It means that this is the way the current should flow through the circuit from higher potential to lower potential. So let's see in first case, as it is flowing from higher potential to lower potential, my E1 should be positive. Then coming to I1 and R1, as it is moving from higher potential to lower potential, my potential should be taken as negative. Same way, I2 is also flowing in a way that it is moving from higher potential to lower potential, and that's how it also should be negative. So my equation becomes E1 minus I R1 minus I2, this is I1 R1 and minus I2 R2 equal to 0. So as we have seen that in this particular loop A, B, E, F, my EMF was positive, that is E1. My I1 R1, it is in the direction of current, so it is negative, and I2 R2 also in the direction of current, it is also negative, and total is 0 according to Kirchhoff's second law. Now coming to another loop, this particular loop which is B, C, D, E, and in this particular loop if we see, the EMF of this particular cell is as the direction of current, that is from positive to negative. Therefore my EMF I would have to take as negative. Now the current that is flowing I3, so my potential drop across R3 will be I3 R3, and my potential drop across R2 in this particular loop will be I2 R2, and the total will be again 0. But you see that I3 R3 is in the direction of current, therefore it will be negative, but I2 R2, this potential drop, actually the current is flowing in this way, so the current flow direction is opposite to the current of I2, so this will be positive. So according to this loop, E2 minus I3 R3 plus I2 R2 equal to 0. So this is the way you can analyze all the potential and EMF summation of the loop using Kirchhoff's second law, and this helps us to analyze when we are taking a complicated electrical network and electrical circuit. We can apply this law and analyze the circuits very easily. The second law of given by Kirchhoff is actually tells us that the energy in the circuit is always same. The energy lost due to the current flow is it's conserved, and energy loss as the work is being done to drive this current. So Kirchhoff's second law actually tells us that there is a conservation of energy while the currents are flowing in this particular circuit.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.